Hello everyone and welcome. Could somebody just let me know that you can hear me okay, please?
Loud and clear, Gerard.
Yeah.
Great, thank you.
Yeah, I can hear you.
Thank you. Hi, yeah, welcome. This is the 14th of our series of webinars, and our aim is to help researchers and practitioners share knowledge and experience in natural flood management. Hi, I'm Gerard Stewart. I'm the communications coordinator for the research programme, and you can probably see that Nick Chappell, who's just turned his camera on, is going to be presenting today. Nick is the lead for the... Sorry, I'm getting some feedback there.
Can you hear me okay?
Yes, no problem.
Yeah, okay, sorry, I was getting echoing. So Nick, who's just appeared, is going to be presenting today. He's the lead for the Q-NFM programme, one of the making up the programme. Just before I hand over to Nick, just a couple of things to go through. So yeah, please keep your microphones muted and videos off to avoid distraction as the webinar proceeds. Actually, Nick, would you mind muting yourself through? Please do ask questions and use the chat function. And we've got Dr. Trevor Page, one of the other members of the Q-NFM team working with Nick, who's on hand to answer some of the questions as the webinar progresses. I do need to let you know that the webinar is being recorded for GDPR purposes, but also so you know that it's available. We'll make it available on our website alongside the other webinars. So yeah, let people know if they haven't been able to attend, or catch up if there's parts you'd like to hear again and listen to at your leisure. So the webinar, the Q-NFM project, which Nick will be talking about some of, is part of NERC 4-year, £4 million program. I can. Thank you. And we're carrying out novel environmental science to improve our understanding of natural flood management, where possible, including quantification. We're looking at a range of NFM measures in different types of catchments, flooding scenarios, and at different scales. And our aim is to improve evidence and understanding for policymakers and practitioners. There's 3 research projects that make up the programme. As I mentioned, we're going to be hearing from Nick about Q-NFM. The other 2 are Landwise and Protect NFM, which are looking at different geographical areas and to some extent different aspects of NFM. Drawing on the expertise of partners is a really important part of our work, and I know Nick's going to talk a little bit about that with regard to his work. And it's really critical for the success of the programme. This webinar programme is really part of that engagement process. So there's some of our partners to give you a flavour of the range and number that we are working with. Okay, well, I think that's probably enough from me. You're waiting to hear from Nick, so I'll hand over to you, Nick. Over to you.
Thank you very much, Gerard, and a warm welcome to everybody to this webinar on measuring NFM effectiveness. So I'm Nick Chappell and will do the presentation, but I'm joined with my colleague Trev Page, who will keep up with some of the chat as we go through the talk. So what will we cover today? So essentially seven topics, though I'm going to focus primarily on 2 issues of particular importance to our project. That is having accurate streamflow measurements, and then exactly how we are trying to measure hydrological change within flood events to support our projects. So dealing with that first point, what is NFM effectiveness? Well, to us, it's quite simply a reduction in peak flow during large flood events. That is our objective of our field data analysis and of our wider dynamic modelling. So most of our work is very Cumbria focused and associated with two sets of projects. First of all, as Gerard has noted, the NERC NFM program, the Q-NFM project, and that is primarily a physics-based modelling project, but has some field monitoring. We also have the CNFM project, which is funded by the Environment Agency, and this is primarily a field monitoring project, but with a relatively small amount of dynamic systems modelling. So there is the current investigator team for the Q-NFM project, and I'm obviously talking to work that is very much a team effort. Equally, we have within the Q-NFM project, as shown with this graphic, a lot of really excellent partners for all sorts of different reasons. Critically, we have the Environment Agency, who are providing an awful lot of data for us, but equally important are a lot of our environmental NGO partners, who are the people installing the interventions within Cumbria. Our remit is measurements and modelling, not installation of particular systems. So why within our program do we have hydrological observations within Cumbria? Why do we need those observations in our view? Three key issues, and I'll try and illustrate each of those very briefly. So first of all, we are part of the Environment Agency's program of NFM pilots in Cumbria, and all of these different pilots are joined together within one network, and what you see there are our monitoring stations and also our wonderful partners who are applying the interventions within the catchments. And the objective of our element is to show exactly how much benefit in terms of flood peak reductions can be gained from the interventions installed. For Q-NFM, our primary objective is to actually show how the NFM effects can be presented as model parameters and shifted within the modelling to represent the effects. So the parameter changes might be, for example, saturated hydraulic conductivity of the ground surface. So today's presentation is not really about the modelling, but it's useful just to have a very brief bit of context. So the way that we do our modelling is, first of all, to undertake baseline simulations of rainfall to flow using all the lovely Environment Agency data. And however good our models are, we always have uncertainties in the parameter sets and the way we simplify our hydrology of the catchments, which we need to reproduce within our modelling and our modelling results. But equally important is that when we shift our model parameters developed in this first stage to then represent NFM-related change, we need to represent that variability that we see within these NFM features in reality. So we don't want to be running theoretical shifts in parameters. We need to base it upon the variability of the way these different features behave. So having good data locally helps us in that quantification and reduction in the uncertainties, constraint on the uncertainties. But the third and equally important reason why we're doing measurements is to make sure, as best we can, that our modelling is consistent with what we know about the way the catchments behave. So we've added measurements to inform ourselves and inform or evaluate our modelling based upon local observations, in our case in Cumbria. In this particular example of this gauging station, I'll come back to some results from that shortly. So moving on to point 4, the importance of accurate stream flow measurement. So that importance equally applies to baseline simulations of Environment Agency data. So this is one of the weirs operated by the Environment Agency, which is in the upper part of the Kent catchment. And critically, the very impressive hydrometric team went to this site and a range of other sites during Storm Desmond and got some direct gaugings. Why is that important? Well, here are those 2 gaugings from that gauging station during Desmond. If those gaugings weren't available, the rating that we would have used to calculate flow for this particular site would have followed that blue line. And as you see with this sort of crude estimate here, we would have simply been 10% under in terms of our observed flows, by which we are then trying to run our models. So there's the revised calibration now incorporating Desmond. So having really high quality data during floods is really important. Now, we are installing and have installed lots of micro catchments, gauging stations at the 1 kilometre scale. And that is equally important at that scale. In other words, accurate stream flow measurements are really important at that small scale. Why do we need stream flow measurements at that small scale? Three key reasons. First of all, that's much closer to the scale of the NFM pilots that we are trying to assess the effectiveness of within Cumbria. Secondly, if we zoom down to the 1 kilometre squared scale, and obviously the agency data, which is an excellent network, is actually at a much larger scale. It's gauging catchments 100, 2,000 kilometres squared and so on. But down at that 1 kilometre squared, the catchments do actually behave quite differently. It's very important that we can quantify that with direct measurements. And then thirdly, while we do need some direct observations on how individual NFM features are working, let's say how much volume they are capturing, we need to know the context of that volume. Is that volume being grabbed on the rising stage and then everything is completely full by the peak, not terribly effective? Or indeed, are these features all full and so on in very small events, and then very large events, there's no additional storage and effect and so on. So we need that gauging at a local scale as a reference for the behaviour. Just to go back to one of those points about catchments behaving really quite differently at that small scale, here we are at the Howgill Fells in Cumbria, and this is what is called the Loon Gorge. This is where the M6, the main railway line going north on the west coast, and the River Loon all try and squeeze through this same valley. Now, as you see from that map, we have 2 micro catchments installed on the Howgill Fells, and if we were to zoom into the very detailed BGS maps of the geological strata for those 2 catchments, we would see that essentially those 2 catchments are on the same geology. It's the Coniston group of sandstones and 1 or 2 other things. So essentially the same mapped hydrogeology. However, if we actually look at the way these individual catchments behave, so this is one of our trapezoidal flumes, obviously at low flow, it's still flowing there at T-Bay Gill. There's one of our rain gauges by which we can do this analysis. We can actually model the rainfall runoff dynamics, and I apologise for all the technical terms that are on there. All I want to draw your attention to are just 2 terms. So for this T-Bay Gill micro catchment, we have a very short, what is called pure time delay. So that's the time between it raining and you getting your first response in the river. And it's effectively instantaneous. It's one time step of our data. Equally quickly, if you look at the residence time of the response, now if this was a purely linear system, now we are modeling with some nonlinearity here, effectively that would be how quickly the catchment dumps all of its water after the peak. It's effectively getting rid of 2/3 of the response within 59 minutes. That's quite a fast response against other catchments in northwest England, which tend to be several hours. So if we move from this site to the southern end of the Howgill, so there we are at the Sedbergh gauging station. So remember, we're on essentially the same geology, and indeed this particular site is much steeper, very steep slope upstream of here. We have actually a very odd response from this particular catchment. So when it rains, actually nothing happens in this gauging station for 8 hours. And then once the system has switched on and you've got your flood, it takes an awful long while to get rid of that water. It's taking 38 hours to come down on that recession curve. Now, we do happen to know why that is likely to be the case. The water is clearly going into the ground, is going into fractures, deep fractures before it's actually coming out. But that affects the way we need to represent our processes in our model, but also the way we need to think about what we would do at those two different sites with NFM features. So why is accuracy specifically important to us? Accuracy in our discharge measurements? 3 reasons. First of all, there is an acknowledged issue about trying to get discharge calibrations from level measurements that we take in a river during higher flows. We know that's difficult. Secondly, what we're about is quantifying hydrological change from a range of different experimental designs. And quantifying hydrological change also requires excellent stream flow quality data. And thirdly, as I alluded to before, we have for our modeling a very explicit uncertainty framework, which means we need to quantify uncertainties for all of our components. That includes the observations, but it's also about trying to constrain that uncertainty to improve that accuracy, so we've got better credibility on some of our predictions. So if I can look at a couple of those in a little bit more detail. So if we, and many of you will appreciate this, try and develop a level 2 discharge rating for a natural stream without some sort of a control structure, a trapezoidal flume as shown here, or maybe a weir, we know we have to dash out into the field every single storm with our dilution gauging apparatus, get to the site, realize we've missed the peak and so on, and have to do it in the next event and so on. So we need many measurements, which are really hard work. They're actually dangerous because that flood might be at night and so on. So it's quite difficult building a rating curve. So our approach to that is always to use pre-calibrated gauging structures. These are Forth River Purification Board flumes that have an established calibration, which if you put them at the right location will conform pretty much to the calibration. Just need a few checks and so on. We tend to use these sorts of structures rather than weirs because they're rather better at handling sediment. You see there's actually sediment in this particular system, and they're also better at allowing the passage of macroinvertebrates, fish and so on, which is important when we're installing these on permanent watercourses. So let's just take you to a little bit of reality here. A very short little video clip from last week of the flume operating, and you can probably see from the writing there, this is actually inside our secret beaver enclosure within Cumbria. So the second reason why we want really good accuracy with our streamflow data is because we're trying to quantify hydrological change from a range of experimental designs. And we are using 4 quite different designs to address NFM. So our type 1 design is where we have one of these trapezoidal flumes upstream of an intervention and also another downstream. We then have other sites where we have an adjacent basin, which is a reference, a control, which is not changed compared to the control basin, compared to the intervened basin. Thirdly, we have a lot of sites where we have a single reference gauging station. So while it's important to quantify how the storage, let us say, is operating, filling, emptying in a particular NFM feature or series of features, it's really important to link that through to what the actual stream is doing to know where that storage is coming in and whether it's intervening on the right size of a vent. And then fourthly, some of our gauging stations were installed well before any intervention, and we continue them after. And obviously, if we combine a couple of these things, for example, type 1 and type 4, indeed type 1 and type 4, what we have is what the ecologists would call a BACI design, a before-after control intervention, the ideal experimental design. Now, we can't actually use that in a lot of locations. Here's a location where we have used a BACI design. So this is in Lowther Park, our Bessie Gill site. Now, historically, the upper part of this catchment had been diverted. All of the flow to this point had been fired down a culvert down towards the River Leith, a tributary of the River Eden. And what the Eden Rivers Trust and Lowther have done is basically cut off that diversion and allow the water to spill across the floodplain to join the old channel, which starts a little further downstream and again ultimately joins into the Leith. And we have, as you see, a second gauging station downstream. So this gauging station downstream we recorded for a year before that intervention and then have continued afterwards. And the gauge, which you see in the bottom left-hand corner, is just upstream of the intervention, and we continue to measure that before and after as our reference. So that's the idea. It's quite an interesting site, this one, in that this is also the site of Lowther's commercial afforestation, only one of 2 sites in the whole of England with substantial greenfield afforestation, the other being over in the northeast of England. So there is our network of primarily trapezoidal flumes, though we do have a couple of Doppler sites in culverts, one here and one shortly going in next week. And that's the range of experimental design. You see, most are within Cumbria, but we also have 1 or 2 out with Cumbria with other partners. So the 5th element of the presentation. So how are we measuring hydrological change within flood events? So before I answer that, I'd like to highlight those hydrological processes that we are particularly interested in with our particular projects. Others are looking at other projects, other different researchers. So we're particularly interested in the effects of enhancing wet canopy evaporation, of enhancing surface storage, whether that be on slopes, including zero order basins, or on permanent channels, or indeed better engaging with floodplains. And also we're interested in how enhancing topsoil permeability in particular locations can enhance infiltration and hence reduce overland flows. So what are the specific interventions that we are looking at, either with our measurements, monitoring and so on, or with our modeling? So we are grouping them within these 6 categories within some technical scenarios for our modeling, and I'd just like to take you through some of the experimental work that we are doing associated with these particular interventions. But I will spend a little bit more time on the hill slope surface storage, in that I want to show you just how we link the way an individual feature behaves relative to the flows in the stream, the local stream. So that first intervention, enhanced hill slope surface storage, so that captures all sorts of types of interventions, from bunds on slopes, whether that be farmland or rough pasture. It could be swales cut into the slopes. In Cumbria, we have these rather unusual things called kests, which are hedgerows on embankments. Thanks to PhD student Ethan Wallace, we're also looking at the potential value of dry stone walls in storage, and of course within this we have peatland restoration. In fact, I'd like to take you to this particular site, which is at T-Bay, that I've already shown you the map for. So we have a site here with some water level recorders. So water level recorders are inside these tubes. These tell us the level, which we combine with a detailed local survey so that we can turn level into volumes held behind these dams. And this is a restored peatland site. This was formerly a heavily eroded gully. Peat has been dragged into the gullies, the vegetation stretched back over the top. But for NFM, the Cumbria Wildlife Trust also installed these dams, copying exactly the designs developed for the moors to the future. And you note immediately downstream of this section, this overland flow section, we have one of our flumes, and as well further down the hill slope we actually pick up the permanent channel and have another flume. So how do we compare the volume we get behind each of these dams with the flows that are going through our flumes? So a little bit of data. So this is any data that I will present, I think, in terms of time series. So I'm just zooming into what this particular dam was doing on one particular day. So this is dam 5. This is the water held here, and this is volume. So what you can see is this dam is actually behaving as we would like it to behave. It started off completely empty prior to the event. As the flows started to see in the flume, it switches the water, and as the flumes empty, then the storage dumps itself so that it's ready for the next event that might come in the sequence. It's not holding a huge amount of water, as you see. It's only holding about a meter cubed of water at any one time. Now you note we've looked at another example there in this plot. That is immediately upstream of the flume there. This particular dam looks to be holding more water, so you'd think that's better, but you might note that the dam is actually holding the water prior to the event. So there's not much additional more storage available, not much freeboard to grab more water during the flood event. So that's really the important issue with that. Now obviously we've got more flow as we go down the catchment, simply because we've got a bigger catchment area. Now of note there, we can compare the timing of the volume against the flows in the river, but we've got different units. Doesn't matter it's liters per second, that could be meters cubed per second, but meters cubed per second and meters cubed are different units. So ideally we really want the same units so we can equate the two together. This is a little bit more complicated, but it isn't really. So all we've done here is take the time series of volume for this dam here and now presenting it as the volume change. So for every 5-minute time step, we're saying, is the volume the same, or has it increased, or has it decreased? And I'm presenting a capture of water here as a negative value. because essentially this dam is taking that water out of the system that would otherwise have fired through that flume at that particular point. The units are identical, as you see here. So what we can see is this dam is grabbing the water on the rising stage and the peak, which is what we want, and it's actually dumping it quite quickly afterwards. And that is the volume that we are capturing just from this one dam against that discharge. We can equate those two things directly. You note at this slightly bigger event down here, that's quite a small volume that it's capturing against what the discharge is doing, and you see it's only grabbing it on the rising stage. But it's very easy to do this sort of analysis even within a spreadsheet. So let's move from hill slope storage to channels where we have leaky dams. So we're using exactly the same methodology for measuring water level, surveying the area that water level will equate to, and just downstream we have a flume. This actually is a permanently flowing channel. It's just a little bit buried. You can't see it. Now, obviously, people are using all sorts of different types of leaky dam design, and particularly so in Cumbria, which is great. We have more different types to look at. So this is a rather more naturalistic dump of timber that we are measuring. If we go to the Flimby site, you see we've got these what we call horse jumps, more engineered type of dam. Again, there is a gauging structure downstream to equate our volumes to. This site is interesting in that it's our partner, West Cumbria Rivers Trust, that is doing the monitoring, and we're just providing a little bit of additional support in terms of analysis and so on. And then let me take you to a third type of dam. So this is at T-Bay. This happens to be on a side channel. This is a demonstration site so people can actually see some of the things that we are doing. This site, it's whole large stems that are dug into the banks, dropped across the channel. You can see the normal flows go underneath the structures. You can also see that perhaps you can see this, we have an automatic recorder in this black tube, but we combine that with some 5-minute continuous 24/7 photography as well. Now this T-Bay site I'm highlighting in that when we go to the main channel, which is somewhere of the order of 5-7 kilometers squared, already on this site, the farmer group who've been building these have put in 77 of these large dams along the course of the river. And you see we have our water level recorders dotted on some of those. And there are some of those dams operating during a flood event earlier on in the year. And you note that these features in many places, as well as grabbing water in the channel, are also better engaging with the floodplain, spilling water onto the floodplain. And I particularly like these sites in that you can actually see the interventions from space. So there's a Google Earth image zoomed into some of those dams, and I say these are the dams that you can see, these like staples in the landscape, holding the landscape together, installed by our farmer friends. So that takes me on to the third type of intervention, which is trying to enhance the way our floodplains are working. Dig swales, adding bunds, better connecting the floodplains, and so on. So most of this work is actually on the Lowther estate in various locations, supported by the agency. And I've already mentioned one of these sites, this Bessie Gill Channel realignment site, and indeed there is a further intervention that they've installed on this site. So our gauging station is just here, and there is this very dynamic storage. It fills and empties associated with flood events, and again we're monitoring how that works against our flume. But we have a number of other sites on the Lowther estate. So that previous gauging station was way over there. We're now at the Whale floodplain. So this is a new intervention where to engage with the floodplain, so we're measuring the volume changes on that floodplain, but critically we're also measuring the flows on one of the two key inflows into this floodplain, so we know exactly when these extra volumes are being grabbed. Are they being grabbed in the flood events, and indeed what size of flood events is this storage effective for? Is the storage only effective in little events that perhaps don't flood people, or is there still effect during much larger events? So that discharge measurement we do think is important. Now at Lowther, so I've moved from that red arrow there across to the main Lowther. So they're also intervening on the main river. So this is a bit of paleo channel on the floodplain, and this is a new intervention to better connect that floodplain. And again, we have monitoring in that area to see how well we can better engage that floodplain. Moving swiftly on to our fourth type of intervention, soil management, very much focused with studies on slowly permeable soils, the soils that are more likely to generate overland flow that will rapidly go down to the watercourses, generate peaks and so on, and looking at ways of enhancing the infiltration, which is obviously one of the roles of trees, but also established agricultural soil management. So what you see in the photograph here is what is called sward lifting, which is a method of aeration where essentially a slit is cut down through the field. So we've been measuring on this field and in other sites permeability across that slit and immediately adjacent in between the slits, and we use Talsma ring permeameters to do that. And there is a little bit of data that's from another site, that's from Gamblesby Village, and you don't actually need very many data points to actually show these differences, because the differences are really quite large. So that's sward lifting. Those data we've yet to publish, but we've been working on another type of aeration called blade aeration, and we have been able to publish that. Again, that is some of Ethan Wallace's work. Now that's rather interesting work in that it's done with Brackenborough Estate near Penrith, and Brackenborough are great in that they've allowed us to install 2 more gauging stations on their land, and upstream of one of those they blade aerated the majority of the catchment so that we can see whether these local scale interventions do impact the flows in our gauging stations. So that takes me to the fifth, the penultimate of our interventions, and that's enhanced wet canopy evaporation that could come from extensive woodland planting. Those of you not familiar with the word wet canopy or the term wet canopy evaporation, the old term is interception loss. So a lot of what we do to inform our modelling, the shift in the NFM parameters, is actually based upon other people's data, published data, and data that we've mined from other studies. And it's presented in what we call our catchment change database. Now, Trev Page has been doing a lot of work in terms of the data to look at whether wet canopy evaporation from trees, which are known to be particularly efficient at wet canopy evaporation, still takes place when we have large flood events. There has been a perception that it's not important during large flood events. So what you see there are data from plot studies, and we're particularly interested in these larger rainfall events and the numbered points, in fact, from UK forests rather than other global temperate forests. So in the data, you can see significant wet canopy evaporation data from woodland and forest. Indeed, if you want to go to even larger events, we can't do that with the UK because nobody's actually measured flood-based measurements on wet canopy evaporation as yet, you actually still see the same story. Significant wet canopy evaporation during the flood events. So the question is, and it's the question that Trev posed within that paper, why is that the case? Well, what Trevor has done is looked at the atmospheric humidity through large flood events in Cumbria. And of course, here's one which we all know about, Storm Desmond, and obviously we're just about to hit the sad anniversary of Storm Desmond, the 5-year anniversary of Desmond. And you can see there's one of these sites, which is at Gisborne, which is actually North Lancashire, where the atmosphere is completely saturated for most of Desmond. That means there will be zero wet canopy evaporation. But if you look at these other just example sites here, while the atmosphere is very wet, it is significantly below saturation, which means there is capacity for evaporation during the event itself, particularly when you combine it with the higher wind speeds during these large flood events. I can summarize that in this diagram, but it's a bit of a complicated diagram. I apologize for that. So where are we on this diagram? Well, essentially in these windy flood events, we're right down here in terms of aerodynamic resistance. And indeed, if the atmosphere is completely saturated, even though we're down here, we're still going to get zero wet canopy evaporation in the event. But as you see, as you go up this plot, okay, as we move up either sides there, you can see as you create a little bit of capacity in the atmosphere, you can have significant rates of evaporation. Now, that is a bit of a complicated diagram. Can I present that as a headline figure? Now, that is actually a very dangerous thing to do because these things can be misconstrued. So I'm going to be as conservative as possible. So if we had an event of 100 millimeters per day, a single event, now that would be serious for Cumbria, and we look at leeward slopes in the Cumbrian mountains, which is where the atmospheric capacity is the greatest from the work in terms of the weather station data. And if that was an area of mature, complete 100% woodland cover, the site that we look at, and whether that is conifer forest or whether that's deciduous forest with not a single leaf, but still with a very complicated branch canopy, it is not unreasonable to get 10 millimeters of wet canopy evaporation from that event, from that analysis that Trevor has produced within that paper. And what does that mean? Well, that could give you, if you were to look at a 1 kilometre squared catchment, something like 10,000 meters cubed, not in this case of storage, but loss, removal out of the system. And I'll come back to that 10,000 meters cubed right at the end of the presentation. We do have a small number of plots where we're trying to get some direct measurements of wet canopy evaporation during these larger events. So these are simple collectors, but an awful lot of them, and the design is very focused into us simply starting the collection of water just before a forecast large event and then going straight afterwards and getting the data straight afterwards. So we're only interested in very large events. Just a little aside, in addition to these parameter shifts that we're taking, we are doing things like measuring water content in various paired plots. So these are some illustrative data from a site near Grange-over-Sands. And Grange-over-Sands has a regular flooding problem for the people who live along Windermere Road here. And clearly the drier soil, the drier topsoil that we're seeing just inside the wood is going to be a function of the enhanced wet canopy evaporation, but also an effect of the drying from long-term transpiration and of course the infiltration enhancement. But it's a little bit of a sanity check when we look at how our models are generating flows within our catchments between these different land uses. Okay, so the fifth and last of our type of intervention is again related to wet canopy evaporation, but it's all of those vegetation interventions that are less than full forest cover. So that takes in all of that wonderful scrub planting that you've seen around Cumbria. Potentially it takes in rewilding, where you've got longer grasses and scrub vegetation, shelter belts, hedgerow restoration, and so on. So most of the way that we're going to deal with this will be as a proportionate effect of what one gets from full forest cover. But we do have some explicit measurements targeting those types of intervention. So here we are in the very headwaters of the Eden catchment at one of our flumes here, and this particular site has received scrub planting. I'm afraid I'm pointing in the wrong direction here. I should be pointing upstream, where you'd see a sea of these Thule tubes with new planting. And if you're interested in perhaps how we install some of these flumes, there is quite a nice video that the Woodlands Trust helped us produce of the way that these are installed out in the natural environment. Again, as a little aside, a sanity check at that very small scale, that plot scale, we are interested in hedgerow functioning, and we're also particularly interested in what's happening to overland flow. Overland flow, rarely do we get the chance to observe it like this. So we are trying to get some measurements, direct measurements of overland flow. Now, this particular site is another of Ethan Wallace's measurement sites. So we're measuring directly overland flow coming off this grassland pot, a replicate a little further downstream, and two other plots that are actually inside the hedge to see exactly what these aggregate effects of the hedge is doing to our overland flow. So what I've shown you there are the way that we try and capture the volumes of water that are being affected by individual NFM features and a distribution of those features. But ultimately, we need to know how we're going to scale that up to what the effects would be at the catchment scale, whether the catchment be really quite small or up to 2,000 kilometers squared or more of let's say, the Eden catchment. Now, most of our analysis is actually on the modeling associated with that, which I'm not attempting to cover within this presentation, but I think there's actually an easier way of looking at this so that we can actually start thinking about scaling up now. And the way that I propose that we do this is actually to look at what an engineer would do now if working for the Environment Agency, trying to put in a traditional engineered storage structure. So I'm giving you here an example from close to Lancaster. This is Garstang Flood Basin. So during a flood event, these gates switch on and capture something of the order of 1.3 million cubed of water intervening on this catchment, which down to this point is about 140 kilometers squared. Now, if you look at a range of intervention schemes where storage is added, what you will see is that, broadly speaking, so this is quite crude, about 1 million meters cubed is added to capture the peaks associated with 100 kilometer squared contributory areas. Now, I can't visualize 1 million meters cubed. I'm sorry, I find that very difficult. What I can visualize, however, is 10,000 meters cubed, which is the equivalent for each 1 kilometer squared of your contributory. And any hiker is quite familiar at looking at an OS map and seeing these blue squares all over the map. Those are our 1 kilometer square. So in other words, if we want a way of judging how much we might need if we wish to reproduce what the agency does for protecting communities, and I'm not suggesting that we are replacing agency traditional engineering. This is a complementary method, but just to give you an idea, this is the level of volume we need to intervene. So, you know, it's maybe a tank which is 100 by 100 meters across and 1 meter deep. So to do that above all of our flood affected communities, clearly that is going to require a substantial amount of public investment, whether that's through the Environment Agency and all the other regulators for the other nations in the UK, or whether it's through DEFRA and ELMS payments, or whether it's private companies such as water companies, national parks, and so on. We need a very large amount of investment to make sure we are delivering what we are hoping to deliver. So what are my final three messages that guide what we do? We certainly do attempt to incorporate always accurate stream flow measurements in our experimental design, because we are trying to see how hydrographs change. Secondly, we do want to characterize variability in the volume of response, and I've only given you really one example of variability associated with those peatland dams, but it's perhaps a good example where the feature actually looks quite similar, and yet it's actually working quite differently. So we need to capture the variability of these features before we run our models. And then thirdly, when we're considering volume change, and I do want to emphasize volume change, just because we've got water sitting in the landscape doesn't necessarily mean it's beneficial to flood mitigation. It's the extra volume that we can capture during the floods that's important, but we need to be considering the number of features of a particular type that we would need to deliver, let us say, 10,000 meters cubed for every kilometre squared upstream of a flood affected community, and very often we're going to need all sorts of different interventions to get close to that. And some interventions, maybe with floodplain storage, we can grab very large proportions of that very quickly, while other interventions which are only going to grab 1 meter cube, we're going to need a huge number of those in the landscape. So with that, I would like to thank you and open up any questions. If I can now stop sharing my screen and hand you back to Gerard. Thank you.
Thanks, Nick. Very interesting, very clear. Yeah, we've got a few questions. Trevor's been very busy answering questions as we've gone through, so thanks a lot, Trevor. Yeah, we've had some questions that people submitted in advance, so we could pick a couple of those perhaps. One is, how does the potential impact of NFM measures vary across England's different catchment types?
So NERC, when they were putting together the program, certainly did think about that. And obviously we are focused in the mountains in Cumbria, primarily a grassland landscape, while the Reading-led project Landwise is focused on very much groundwater dominated catchments with a lot of arable agriculture and interventions associated with that, while Manchester's focused very much on the peatlands. We've just got 2 small peatland sites there. Understanding from the way we intervene on peatland is going to be very important. So I think it is going to be very important that we integrate all of our results from these different programs. But what I would just illustrate from what has surprised us really working in Cumbria is just how important the groundwater story is to a lot of our catchments in Cumbria. It isn't an impermeable system, Cumbria, so many of our catchments have a strong groundwater story. And if you were to take that example I showed right at the beginning of essentially the T-Bay site with a very flashy response as opposed to the Sedba site with a groundwater response, with T-Bay we need systems to switch on very quickly and to grab that water and to empty very quickly. While Sedba, we don't really want features to switch on very quickly. We need to wait until that flow is built up and we've got that catastrophic amount of flow, and we need very big features there to grab those volumes of water, because once that Sedba system is switched on, it is not going to stop and it is going to keep pouring water down to that Sedba community. So the different differences in the way our catchments are behaving, I think, is very important in terms of the design of the features. Hopefully that says something about those differences between catchments. Thanks,
Nick. Another pre-submitted question was, could you say something about the consideration of effectiveness over NFM asset lifetime with a view to planning best value investments, aligning NFM whole life costs asset thinking to traditional FRM assets?
So thinking about whole lifespan costs and the behavior of the features is obviously something that traditional engineered structures will have been through. So it is certainly important that we consider how our NFM features are going to behave in the long term. Our simulation shouldn't be just looking at an optimal delivery. Obviously, if we plant trees, it's going to take 30 years maybe before those trees are going to have significant wet canopy evaporation. Equally, with some of our leaky dams, if they're very well engineered, maybe those things are going to need a lot of maintenance to maintain that engineering, while some of the more dumps of timber, if I can put it that way, the more naturalistic systems, we put them in there and we leave them, and as long as we haven't put them near a culvert or a bridge and so on where the timber would make a problem, essentially they are much more low maintenance. So we do need to look at perhaps the negatives sometimes of the features, so that particularly we can get buy-in from everybody, from the landowners who are quite sensitive to these things, but also people paying for these to be built and thinking about maintenance. So that whole lifetime behavior is really and effectiveness is really rather important. Yes.
Thank you. A question that Trev asked, if you could answer, was how much does one of these monitored trapezoid flumes cost to install and then monitor?
Okay, so I mean the core of the flume really is the flume itself. And the flume is only about £450, which is actually not a lot really, with delivery costs from that Genesis Composites link I did actually put on the slide there, so if people wanted to buy that. So that's the critical element that you need to do. Now, how you then measure water level is entirely up to you. So you can do it really quite cost effectively with these cheaper water level recorders if that's all you need. Now, we have a slightly different remit in that we have a large network and it's quite difficult to maintain. So we've bought systems with full telemetry, so we can monitor what those systems are doing, so we can make sure we can maintain them. We also share that data with Cumbria County Council and with the agency in terms of flood warning, as some of those sites are actually quite useful in terms of flood warning. So our systems are much more expensive. So our systems are about 4K, which adds the rain gauge, the logger, and the telemetry license for 3 years, and so on. But it's a system we find reliable and cost effective. I mean, if anybody wants details of any of those particular systems and so on, they just need to send me an email, and I quite happily send those details. There's nothing confidential about it.
Thanks, Nick. I think unfortunately we've run out of time now, so I've got a minute to quickly wrap up. So thanks very much, and yeah, I'll just wrap up. I've got a slide to share. So yes, thanks very much, Nick and Trev. Thanks to Nick for a great presentation, and Trev for keeping on top of the questions. If you do have questions that have come to mind and you didn't get around to asking, or you would like more on them, Nick's kindly offered to respond by email. So there's his email address, and I saw Trev put his in the chat. The recording of the webinar will be available on our website in the next couple of days. The next webinar is next year on the 21st of January. So John Hollis from the Environment Agency, and he's the NFM program manager there, is going to talk about what we've learned from the DEFRA £15 million pilot program on NFM. And just one other thing to say, we've just published our latest newsletter, and I'll put a link to that in the chat, but you can find it on the website. If you haven't received that and you'd like to see it and indeed sign up for future ones. Yes, so that's all from us. Thanks again to Nick. Thanks to all of you for joining and for your questions and interest. Hope we'll see you again on the next webinar next year. And so happy Christmas, and let's hope 2021's a bit more straightforward than this year. So thanks again, and that's all. Goodbye.
Thank you, Gerard, Trev, and all for listening. Goodbye.